Welcome. Today, we'll dive into 5 algorithms that change the way machines make decisions, from drawing simple lines to bending the geometry of data. We'll see how machine learns to separate what's different. Our first stop in 1958 with David Cox. Before him, linear regression tried to predict everything, but sometimes it gave impossible answers, like probabilities below 0 or above 1. Cox solved this with the logic link, keeping predictions in the real world. Think of a logistic regression as a funnel. It squeezes any number through an S-shaped sigmoid curve, turning messy into a neat probability between 0 and 1. But how does it learn? Using maximum likelihood estimation. It's like climbing a mountain, searching for the coefficient that makes observed data most likely. In 1967, Cower and Hart had a different idea. Instead of learning rules, why not just remember the data? This is an instance-based learning. Classify a point based on the closest known example. K&N decision rules. Simple rule. Check your K nearest neighbors and go with the majority vote. This breaks the feature space into neighborhoods, called Voronoi cells. Machines don't need formulas, just neighbors. The neat part, even a simple one neighbor classifier has a solid guarantee. Cover and Hart showed it can't be worse than twice the base error with infinite data. A proof that simple can be strong. Decision trees. Fast forward in 1984, Leo Brinman introduced CART. Instead of curves, he used step-by-step decisions, mimicking human reasoning with a series of yes/no questions. Decision trees, how they split. The secret engine is Gini impurity. Trees obsess over purity. Each split searches to divide messy data into neat, uniform groups. Decision tree. Here's a practical split. The algorithm tests every threshold. Split 2, for example, perfectly separates the data, turning confusion into clarity. Random forest. Single tree are fragile. In 2001, Bremen introduced random forest. Multiple trees work together, smoothing out mistakes and making a stronger, more reliable model. To make trees unique, we use bagging, sampling the data differently for each tree. Each sees a slightly different world, adding diversity. Even that isn't enough. Each split looks at only a random subset of features. This prevents any single feature from dominating the decision, letting the forest work as a team. In 1995, Vapnik and Cortens has a geometric vision, support vector machines, focus on the best separating line or hyperplane, ignoring probabilistic entirely. SVMs don't just draw a line, they maximize the margin, the street between the classes. The support vectors are the points that truly define the boundaries. What if? Kernel trick. What if data is tangled? We wrap it into a higher dimension using the kernel trick. What couldn't be separated in 2D becomes easy in 3D. Every algorithm ask the same questions differently. How do we draw the line? Probability, memory, rules, consensus, or geometry. Each is a philosophical approach to classification. Trade-off exists. Trees are clear and explainable. Random forests are powerful but less transparent. You often gain predictive strength at the cost of clarity. Over 50 years, our boundaries evolved: smooth curves, neighborhoods, steppes, forests, and wrapped main folds. This is the visual journey of machine intelligence. In the end, these 5 approaches balance rigidity with flexibility. They are coordinates in the mathematical universe we explore as researchers, guiding how machines see the world.